Hi. Holiday aside, I've been struggling for the last week with some pretty significant audio problems. Things that sound like this. 1.1 times 0.01. Anyway, turns out that in my Linux distribution, pulse audio and pipewire do not play well together, and it took me a week to figure that out, along with a number of other issues related to my audio capture device. So, long story short, it's taken me longer than I want to pull all this together. I have quite a bit of footage, but what I don't have is good audio to go with it. So there's going to be a lot of voiceover for the next couple of videos while I try to get through all of this and get you all of the content that I've created. In the meantime, I have taken delivery of all the components I need for the registers, and those are sitting aside until I can get everything caught up again. Let's get into it then. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. This video covers the clock module cleanup. There is the single-step bounces, which the diagnosis of which I had recorded back in October, and I'm just now getting this into a video. This was before I started having audio problems, so this is original audio. And then I've got a new clock module variable resistor, which is a little bit easier to turn, hopefully not tearing up the actual resistor as I'm turning it. First, the single step bounces. Okay, with the scope out, I want to start measuring a little bit here. And I'm going to measure this clock signal here. So the clock signal is coming from the clock module up here to this latch signal here. I can plug that in there and capture that because I've got that jumper that runs, that white jumper that runs across. And I've got this set up so that on the rising edge, it should trigger somewhere about 1 volt. So you can see the clock happening here. And what I'm looking for is to see if there's anything that really bounces in here as I'm continuing to tick this. And I'm going to go a little bit faster, and it looked like I did see something that looked incorrect. As I'm continuing to do this, yeah, every once in a while I get what looks like a bounce. So I'm going to change this to be 1 millisecond per division, and I'm not seeing anything at that speed. 100 microseconds per division. And I just caught one there. Okay. So that's coming straight off the clock, which means that my clock module needs some updates. In particular, I believe it's going to be this register, or I'm sorry, this resistor register. This resistor here that needs to be updated. I need to actually check the schematics on this. So the bounce problem is not in my circuitry here for my register. My bounce problem is actually in my clock, and I need just some additional delay built into this. So I'll note that. We'll come back and we'll do some updates on that. At the same time, I probably do some other work with the clock. So I just have to right now understand that I might get a bounce. Now, if we go back to the datasheet for the 555 timer, I use the monostable operation mode for my single step. And there is some math here at the bottom that says that for a period of 1.1, the resistance of resistor A and the capacitor C, you multiply those three values together and you end up with the time it takes to reach the 2/3 voltage threshold. And I tried really hard not to do any math when I originally put this together, and that didn't work out well for me. So let's take a look at the math. So let's first start out looking at what I've actually got on the board right now. The capacitor itself is a 0.01 microfarad capacitor. The resistor is a 5.1 million ohm resistor. So if we do that math, we end up with 1.1 And then the capacitor is 0.01 times 10 to the minus 6, or micro. The resistor is 5.1 times 10 to the 6, or million. 10 to the minus 6, 10 to the positive 6, those two cancel out. So we end up with 1.1 times 0.01 times 5.1. Or 0.0561 seconds, or 56.1 milliseconds. Okay, so let's test this. I have the oscilloscope hooked up. If I push the manual clock pulse a number of times, I can stop the oscilloscope and take measurements of the time, basically the duty cycle of the clock cycle, the period of time where the clock is high, and compare that against my calculations. Here's one where I have 70 milliseconds. And I have another peak over here that is 64 milliseconds. So what would happen if I was to change the capacitor to be a 0.1 microfarad capacitor, or 10 times the size of the previous, and change the resistor to be a 2 mega ohm resistor, or less than half, roughly 40% the size of the previous resistor? Let's do that math and figure out what my duty cycle would be, or how long the clock will be high. So I end up with 1.1 times 0.1 times 10 to the minus 6 for the capacitor, and then times 2 times 10 to the 6 for the resistor. Again, 10 to the minus 6, 10 to the positive 6, those two cancel each other out. So we're left with 1.1 times 0.1 times 2, or 0.22 seconds, or 220 milliseconds. Just shy of a quarter of a second. I think that better suits our needs. All right, let's make those changes. The first thing I'm going to do is I'm going to pull out the 0.01 microfarad capacitor and replace it with the 0.1 microfarad capacitor. A quick check after that change shows that the LED is staying lit for almost a full second. I'm not going to measure it, but it feels like about a second to me. So we need to reduce that, and to do that we're going to change the 5.1 million ohm resistor to be a 2 million ohm resistor. And then making that change, that feels more like the quarter second that we were anticipating. Let's test that. Now, setting up and going through the same test sequence again, this time measuring the duty cycle, or the time the clock signal is high. I end up with 274 milliseconds. Now, compared to the calculated 220 milliseconds, I'm actually okay with that, because the resistors have a 5% tolerance and the capacitors actually have a 20% tolerance. So swapping out the capacitor one for another, it's entirely possible that I end up with a longer delay. One of the other things I've been looking to do for a while is replace this potentiometer with something of a little bit better quality that will turn easier, because I practically have to twist this thing out of the board to get it to adjust. And so I want to work on getting that soldered up so that I can put it in the board and replace this one. To do this, I've got just a breadboard here that I'm going to use to hold things steady, and I've got an 8-pin pin header here. And what I'm going to do is I'm going to drop that in there in order to support this. basically to have the whole thing in the breadboard so that the pod is supported and straight when I solder it. And then I wired up or twisted up this little spring-like contraption, and the point of that is to go over the barrel of the potentiometer so that it's properly supported as I solder it. While the soldering iron is warming up, I grab some flux and throw some flux on the pins. Not that it's necessary, but I'm trying to make sure I've got some good solder peaks. Soldering the first pin goes okay. You can't really see what I'm doing, and the angle is kind of difficult for me. So I grab something to try to prop that up a little bit to make sure that I can get a little bit better angle on it. And the other pins go without a hitch too. Next, I trim off the extra pins. And then when I place that into the board, I have to relocate a wire and a resistor. The resistor and the wire line up one row apart from each other, where this variable resistor now lines up 2 rows apart between each pin. Okay, coming up next, I'm going to define the assembly code operations. This is going to give us a lot of context for the things that come next. I also have everything to assemble the PCB for the registers, and I'm going to start that after we get the opcodes and the assembly language defined. I still want to move the clock circuit into KiCad, although I may or may not order a PCB for that. And then finally, I still need to add a line driver to the test harness. And that'll be in an upcoming video as well. Thank you. We'll see you soon.